Welcome to AI Frontiers, a deep dive into machine learning research. This episode synthesizes 28 papers published on April 25, 2025, exploring breakthroughs in generalization, fairness, and efficiency. Key themes include trustworthy AI, reinforcement learning, and generative models, featuring seminal work from Wang and colleagues, Raja and team, and his research group. Machine learning, classified as CS.LG in the ArXiv preprint server system, focuses on developing algorithms that autonomously learn patterns, make decisions, and improve through data. This field powers critical applications like image recognition, natural language processing, robotics, and scientific modeling. Current research challenges center on improving generalization capabilities, ensuring fairness, and enhancing computational efficiency. The first major research theme examines generalization and robustness, bridging theory and practice for more reliable models. Wang and colleagues from 2025 link imitation learning performance gaps to information bottlenecks in neural networks. Volta's team axiomatizes uncertainty quantification in regression tasks. A key insight reveals that output entropy plays a critical role in helping stochastic gradient descent escape sharp loss minima during training. Trustworthy AI emerges as the second key theme, focusing on fairness, interpretability, and model calibration. Nasiri's 2025 work develops novel methods for testing individual fairness in graph neural networks. DARE's research formalizes three distinct types of calibration and their connections to algorithmic fairness. Quintanilla introduces local statistical parity for building fair decision trees directly during construction. Efficient training and inference forms the third research theme, addressing the scaling challenges of real-world deployment. Naganuma's team achieves 18 to 24% reductions in distributed training overhead through their pseudo-asynchronous local SGD method. Silva accelerates partial differential equation solvers by 85% using online learning techniques. This research highlights the critical trade-off between synchronization intervals and convergence stability in distributed systems. Reinforcement learning and control represents the fourth major theme, translating theory into practical optimization solutions. Pettyboy demonstrates learning diverse behaviors from offline demonstrations. Mir combines deep Q networks with SHOP explanations for optimizing UAV handover decisions. A notable challenge identified is the computational overhead introduced by interpretability methods in real-time control systems. Several pivotal advancements emerge across these papers. Raja's team enables zero-shot transition path sampling in molecular systems using repurposed diffusion models. He demonstrates how neural collapse geometry boosts continual learning performance by 6.7% on benchmark tasks. Naganuma's pulsed method outperforms standard distributed data parallel training while maintaining theoretical convergence guarantees. Methodological innovations drive these breakthroughs. Wang employs information-theoretic bounds to guide encoder fine-tuning strategies in robotics applications. Raja reformulates path sampling as an on-Sitter-Mock-loop action-minimization problem, allowing pre-trained generative models to handle molecular systems. He aligns feature distributions to neural collapse geometry, creating more stable representations for continual learning scenarios. Examining seminal work, Wang's 2025 paper addresses the generalization gap in imitation learning. By analyzing information bottlenecks and output entropy, the research provides theoretical bounds on performance. This work significantly influences robotics by offering concrete guidance about when to freeze versus retrain encoders in transfer learning scenarios. Raja's groundbreaking 2025 paper introduces zero-shot transition path sampling for molecular systems. The method minimizes on-Sitter-Mock-loop action using pre-trained generative models, producing physically realistic molecular trajectories without task-specific training. This innovation opens new possibilities for large-scale computational chemistry applications. His 2025 research applies neural collapse theory to continual learning challenges. By dynamically aligning features to form equiangular, maximally separated class means, the method achieves a 6.7% accuracy boost on VTEB benchmarks. This approach effectively mitigates catastrophic forgetting in class incremental learning scenarios. Looking forward, the field is advancing along three key directions. Robust generalization research seeks to better align theoretical bounds with practical training through entropy-aware methods. Trustworthy AI requires development of scalable fairness testing and calibration tools. Efficiency innovations must address hardware-aware optimizations for exascale computing demands. 3 key takeaways emerge from this research synthesis. First, Wang demonstrates that effective generalization requires output diversity, not just input scaling. Second, Raja shows how pre-trained generative models can solve complex physics problems without additional training. Third, he proves that neural collapse geometry provides stability for continual learning systems. This presentation was created through an AI synthesis process. Content generation utilized GPT model DeepSeek Chat, with text-to-speech synthesis via Amazon Polly. Visual design assistance came from Grok image generation, and all material underwent human review for accuracy and clarity. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from ArXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening.